Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on October 16, 2025, about 6 days ago. The headline result is a proprioception-only policy that enables compliant human-humanoid carrying and cuts human effort by 24.7% while keeping the load stable. The paper is titled, Learning Humanoid Coordination for Collaborative Object Carrying. And as we will see later, the implications for deploying humanoids alongside people are quite promising. In short, the method fuses leader and follower behaviors, needs no external sensors, generalizes across objects and terrains, and even shows a 27.4% average improvement in a 23-person user study. Alright, the introduction highlighted a proprioception-only policy that reduced human effort while keeping loads stable. Figure 1 presents real-world snapshots that illustrate the range of coordinated behaviors the policy supports. The top row shows full-body collaboration with an 8-kilogram box, which includes lifting, walking, and turning while maintaining height. The middle row shows collaboration on a ramp with a 5-kilogram box, so balance and foot placement matter. The bottom row shows leadership, where the robot guides a cart up a slope. So, while Figure 1 showed real deployments, Figure 2 presents the 3-step pipeline that produces compliant collaboration. The graphics first depict whole-body controller training that tracks commanded motion using only proprioception, which stabilizes walking while positioning the hands. The center pathway then adds a residual teacher that uses privileged object motion to refine actions for coordinated carrying. The right panel distills that teacher into a proprioception-only student policy, so the final controller runs without external sensors. Okay, the previous figure distilled the residual teacher into a proprioception-only student. Table I lays out the reward terms that shape collaborative behavior. Linear and yaw velocity tracking both carry weight 1, so the robot matches object motion. A small z-axis velocity penalty reduces vertical wobble, while a strong height difference penalty, weight 10, keeps both ends level. A light force penalty limits horizontal push and pull, and phi denotes an exponential shaping of tracking errors. Well, the previous table set the rewards that encourage stable collaboration. Table 3 reports simulation metrics and shows consistent gains for the distilled policy. Cola L achieves the best tracking, with linear and angular errors around 0.102 meters per second and 0.098 radians per second, and height error about 0.038 meters. Cola F is close behind, around 0.109 meters per second and 0.118 radians per second. Both variants also reduce average external force to roughly 12 to 15 newtons, which implies lower human effort. So while Table 3 reported simulation metrics, Figure 5 quantifies how the policy responds to forces and maintains height. The top left plot shows base velocity rising sharply once external force exceeds about 15 newtons, which signals compliant following. The top right plot shows pelvis height settling smoothly over time without oscillation. The bottom left bar chart reports lower minimal forces needed to move the robot. The bottom right chart shows the smallest height difference during collaborative carrying. Wrapping up, 2 takeaways stand out. A proprioception-only policy that unifies leader and follower roles cuts human effort by about 25 to 27%, and the distilled controller stays stable across objects and terrains without external sensors. The broader implication is safer, cheaper deployment of humanoids for real assistance in homes, hospitals, and factories. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.